Okay, hello everyone. Thank you for the invitation to give this talk. So my talk will be half practical, half theoretical, but all of it will be related to Fourier analysis in some sense. So I will talk about some smoothness properties of neural networks. Most of the slides that you will see are done by my students. And what I present here is based on three works, one by myself, one with my master student Oshuat Var, and one with Amir Hertz or Pearl, Olga Sorkin-Hornuk from ETH, and Daniel Cohen-Or. And so what I will try to convey in the next 45 minutes, if time will permit, is we'll start with a bit of motivation about neural implicit functions. Then we will go about some theory about generalization in learning of smooth mappings. Then we will see how this theory helps us to get some new regularization or some non-regularization to improve robustness to label noise in neural networks. And then we will talk about a new encoding technique to improve implicit learning in neural networks, a new technique that we call SAPE, and we will show some visual results. So the motivation for the talk is neural implicit functions. So if you're not aware of neural implicit function, the idea is very simple. You want to represent a certain image, let's say. So you train a neural network that receives as input coordinates, let's say the XY location, and need to give you as an output the RGB value of the image. So this is a very simple mapping from the coordinates in XY to the RGB value of the image. So in recent years, several works studied this problem and tried to see whether we can learn with a network such a mapping. And then if you learn just from the XY coordinates to the RGB, you get something that is smooth, but not really what you want. And if you go to some higher dimension, like using some Fourier features, you are able to learn things in a better way. Now, this idea of learning from coordinates to values can be used for multi-view synthesis of things. So for example, if I have multi-view images of the same scene, so I can map from XYZ to the value, and then you can reconstruct 3D shapes like in the known NERF work. And there are many works that try to learn this neural implicit function, either in a pure implicit way where you get coordinates and get as an output the value, or in some hybrid way where you code or split the space in some smart way. And then using this neural implicit functions, so you can also work not only with images, but also with contours. So for example, we can move from this circle to this nice dinosaur, or we can take a mesh, move it to another point cloud, and get the mesh on the new point cloud. So our setting is simple. We have an input, which is coordinates. We have some hidden layers, and we get the value at the output. And we train the network and with lots of data. So for example, we can do it in one-dimensional setting, and then we have the x dimension, which is px dimension, which is the input, and the output is the value of the function. And then at the output, we get in the network this learn function. And interestingly, many times the network learn in a smooth way to interpolate the points. So the question that I will try to answer in the first part of the talk is why we get this nice interpolation from theoretical perspective, or how many points we need to learn this interpolation. And this works also in 2D, so we can subsample an image, and at the output get interpolation also between so we train the network with XY coordinates of the image and give it as output the values at these coordinates. And then at the test time, we also sample location where we didn't see at the train time, and we get the whole image. So, and again, you can see that the network is performing a smooth and nice interpolation. So I repeat the setting, you give the network the XY locations, just the coordinates, and then give it as an output the RGB value, which is basically the sparse things here. And then you give the network also coordinates that it didn't see before, and the network learns how to interpolate things in a very smooth and nice way. And you can do the same also in 3D. So you can take this subsampled 3D map, 3D shape, and also represent it in the same way using a network. So the implicit representation basically get coordinates and give you an output. So it can be a value for an image, can be occupancy for 3D data, or just magnitude for 1D signal. Now, the first question that I will try to answer is why we get this nice interpolation. And also, beyond the fact of why we get this nice interpolation is how many examples we need to generalize in a good way. So this conference is about Fourier analysis, so just repeat a bit of a basic concept that we know. So we define a Fourier series in the following way. Gx is basically the sum of some exponents, and each value can be calculated using this simple formula. And then if we take the derivative, we get this sum. And we have the Parseval theorem that says that the sum of the Fourier coefficients is equal to the integral of the function. And in our setting, in the beginning, we will assume that we have a univariate network. Univariate network means we get single input and give single output with some WL and some biases. And we will assume also that we have a bounded input domain between 0 and 2 pi or 0, 1. And in most of the domains that we work with, bounded input domain is something that is natural because, for example, if you look at an image, so it has a bounded domain, and basically almost in any setting that you work with, we have a bounded domain. And the last thing that we'll assume that we are in the realizable training set, which means that our network is able to overfeed the training data. So when we train the network is able to calculate exactly for each input xn the training value that it got for xn. And then we'll assume that we have some sampling pattern. We will consider both uniform sampling or just random sampling, and we'll see what we get in both cases. So let's, with less samples than what we have seen before. So you can see that if I have this function f of x, and I train a network just with these samples, so I don't get exactly fitting of this function, but I get something different. I get a nice interpolation of the sampled points, but I don't get something that is exact reconstruction of the original function. And the question is how many samples I need to get this exact reconstruction. And the second question is why we get this nice interpolation. So we are not the first to study this question. So Savarese, so among others, Savarese in 2018 showed that finite infinite width unimodal networks. For such networks, the following property is bounded. And if this property is bounded, it means that the network is performing a first order spline interpolation. Williams et al. Extend this to second order splines. It showed that under some NTK assumptions, we get that we have a second order spline interpolation and not first order spline interpolation. And Onge et al. Extend the first result to the multidimensional input. Now here we're not going to the technical details, so we just present the results. But in our work, we added, so in our work, we showed that the same smoothness hold also for finite width unimodal networks. I will not present that, but we proved that. And then we try to ask when we get generalization. So the assumption that we made is that the mapping that we have is band limited. What I mean with band limited mapping, so in the one-dimensional case, band limited mapping is very easy. It means just that this function is smooth. But in classification, band limited mapping is something like that. So let's assume that you try to separate 2 digits from MNIST. So what I did, I took 2 digits from the MNIST. If I remember correctly, I took 4 and 7. I projected them to two-dimensional space using PCA. And then I trained the neural network to distinguish between the digits. And this is the learned mapping by the network. So here in yellow, it means that we get class 1. In blue, we get -1, and here we get something in the middle. Now, if we take this grid of the network and we calculate the FFT of this grid, so basically this is a mapping function from 2D to a decision, then we get this Fourier. Then we get this Fourier transform of the map. And what I mark here is the 99 percentile of the magnitude, the 95 percentile and 90 percentile of the magnitude. So basically I mark where we have a 90%, 99% of the magnitude. So this is in blue. And then in yellow, we have 90%, the 90 percent of the magnitudes that give me the number of magnitudes that give me 90% of the magnitude of the function. So basically, we see that this mapping that separate the data is band limited. So basically, this assumption that mapping is band limited in classification case when you apply neural network is a valid assumption. And with this, we get the following theorem. We get that if we have a finite width univariate network that has bounded weights, either in the Frobenius norm of the weights or in the spectral sense of the weights, then if the training data is greater than 2k plus 1, where 2k plus 1 is the number of non-zero Fourier coefficients of the mapping that we learn, then the error of the approximation of the network go over 1 over n to the time 3. So we get here, I think maybe this is the first generalization bound that show that the error goes down by 1 over n to the power of 3. But then you will tell me, okay, but we know that in general, generalization bounds go like 1 over n and not over 1 over n to the power of 3. And the answer to that is if we go to the higher dimensional case, so the multi-dimensional case, and add not unimodal functions, but functions with d-dimensional output, then the error go to 1 over n to the power of d plus 2 divided by, and then asymptotically, this behaves like the regular generalization bounds that you have from other works. So basically, our work revealed dependence on the dimensionality, revealed the dependence between dimensionality of the input and generalization, and I don't think that such relationships were presented before. Now, the theorem here that I present for the unimodial case that show a relation of 1 over n to the power of 3 is for a uniform sampling. I assume that we are doing uniform sampling. But we know that usually if you train a neural network, so in implicit functions, the case that I presented before, so if you take an image, you can uniformly sample it. But if I just have a training data and I want to train a classifier like in MNIST or CIFAR or ImageNet or something like that, so we don't uniformly sample the data, but we rather randomly sample the data. And the question, what happens when we sample the to the sampling pattern that we have performed?
There was a short lag, I think. But,
what?
Okay, it's fine now. Okay, I'm sorry. We just had a short lag where we couldn't hear you anymore, but I think now it should.
Sorry. Yeah. So in the non-uniform case, so if you sample in the non-uniform case, in the 1D case, so basically the sampling pattern corresponds to some Fourier frame instead of orthogonal Fourier representation. And then this Fourier frame has a condition number kappa. And then the sampling error depends scale with kappa squared. And then we check numerically what happens to the generalization error. So with uniform sampling, if you look at the error as a function of, so we took a function, we trained a network with different number of samples, and you can see that the error of the network, and it goes like 1 over n to the power of 3. And then we train something with random sampling, and you see that the error is a bit worse, but it's still similar to 1 over n to the power of 3, but you have this kappa factor. And in general, this may explain what we see in active learning or other things when you try to do farthest point sampling of the data to get better performance with smaller number of samples. So basically, we see here what we see in practice, that when you uniformly sample the data, you get better results when you just randomly sample it. So this is the first work. I will not go into the proofs to the sake of time, but you can find everything in the paper. It appears on my website or the Google Scholar. The second work is related to robustness. So now the question is, okay, so we know that if we have a band-limited signal, so we know that we can band-limited mapping, so we can get so the error in the learning of the network scale quadratically in the one-dimensional case with respect to the number of samples. And now the question is, what happens if we have noise in the system? So we are still with the same setting. And then if we train a neural network with L2 loss, and we have the example xn, so let's look at this learning problem. So let's assume that you are minimizing things with the L2 loss. So I have our function f that we are trying to learn, and we have the network phi that we are optimizing. Now let's again look at the unimodal case just for the simplicity of the discussion, but we can extend the things to the multidimensional case. Details appear in the paper. So, so we look at the network and we try to optimize the distance between the sample that we have xn of the network. This is like in the unimodal case, this is just a coordinated sampling. And we have the network f, and then we have the function f that we're trying to approximate. So we are minimizing this distance. If we have a smoothness term, like penalizing the derivative of the square derivative of the network with integral, then basically what we're doing, we're penalizing the network to be smooth. Now we can take this term and transfer it to spectral domain. So basically this optimization, if we optimize this optimization with respect to general phi, and we assume that this phi can be represented with some Fourier series, and we assume that f can be also represented with Fourier series, basically we get an optimization with respect to the Fourier coefficients of the network and the Fourier coefficients of the function that we are approximating. And we get this optimization problem. And this optimization problem we can solve with kind of a closed form solution if the number of samples go to infinity. In this case, the coefficients that we have dk scale as ck, which is the coefficient of the two functions that we're trying to approximate, divided by 1 plus lambda k squared. And for finite n, we can prove that it's order of 1 over lambda k squared. So what we see here from this analysis is that if network, like if basically we are learning a general function with this optimization that has no bound, that is not constrained by the weights, then basically we are learning first the low frequencies because we are penalizing more the high frequencies. So if you're learning first the low frequencies, because of this penalty, then basically if we look at one-dimensional case, if we look at the function fx, which is the blue one, and then we will look at a network that is trained with noise. Let's assume that instead of being trained with fx, we are trained with fx plus noise. So we know that the noise, so if we look at fx, we see that it's band limited. If we look at the noise, we see that the noise is spread equally in all frequencies. So if we can force our network to learn first the low frequencies, basically the network will not learn the noise and will filter the noise out. So the question is how we can train a network with this regularization term. Notice that the regularization term penalizes the Jacobian of the network. So the equivalence that we have between this optimization term and this optimization term depends on optimization that penalizes the Jacobian of the network. But notice that here the penalization that we have on the Jacobian is over the whole domain. It's not penalization of the Jacobian, just over our training examples. We are penalizing the Jacobian over the whole domain. Therefore, a trivial alternative to the smoothness regularization that we apply in reality is to use Jacobian regularization. Yet the Jacobian regularization by itself is only a local regularization because it applied only to the example. So the question is whether we can upper bound the Jacobian. So with the Solich et al, we bounded the Jacobian and have shown that it's smaller or equal to the product of the spectral norm of the weights of the network, and this is bounded by the Frobenius norm of the weights. So basically, if we apply weight decay in the network, we are basically bounding the Jacobian whole the network, and therefore weight decay, weight regularization decays high frequencies, and we are expecting to have a natural robustness of neural network noise, which is something that we see in practice. So for example, if we train a network basically with weight decay and you train it with uniform noise or flip noise, you can see that at the beginning, the Jacobian is low. And then once you train it with more noise, the Jacobian increase, which means that if you train a network to learn noisy examples, then network become less smooth. So if you want the network to overcome the noise, you need to make it smoother. So one strategy is to add early stopping, which prohibits learning the noise. Another strategy is trying to have something that bound the Jacobian. So there are many ways to bound the Jacobian. As I said, one way is to do weight decay. Another way is to try to bound the spectral norm of the weights, which is something that is easier to do. So it's not something that's more complicated to do, but it's a tighter bound. Now, instead of just bounding the spectral normalization, so instead of bounding the product, we will bound each separately. And basically, we will, instead of having a lower bound, upper bound, we will just assume that the spectral norm equal to 1, and we will use spectral normalization. Because we use spectral normalization, and this is a tight bound and not a so this is just normalization and not regularization. So we will apply usually the spectral normalization also with weight decay. So let's see the effect of the spectral normalization. So we tried it on several data sets, CFR 10, CFR 100, MNIST, and also on Fashion 100. Details are in the paper. And first of all, we have seen that when we apply no regularization, we get very high Jacobian. And then once we apply L2 regularization, we reduce a bit the Jacobian. When we apply a very strong L2, we reduce it more. But when we apply L2 with spectral normalization, we reduce the Jacobian the most. Now, and then we checked whether this corresponds to better accuracy. And then we have seen that when we apply L2 with spectral normalization, we get better results than we apply L2 or only strong L2. And we tested it for uniform noise, flip noise, for CFR 100, for MNIST, and in all of them we got improvement for L2 plus spectral normalization. So we get that spectral normalization improves the accuracy, and this follow our analysis. So what I've shown so far is that basically we can use smoothness properties of neural networks to understand better their generalization, and also to derive a better regularization technique that can improve results. In the paper, we also show how we can use this spectral normalization also with mix-up and with other regularization techniques that are known for level noise. Okay, now in all what I presented now at the beginning, so basically when we have the unimodal case or this simple function that I presented, so we have coordinates that are mapped to an output, or in the classification case, so it's more complicated, our theory still holds, but if we just look at unimodal case, we have one coordinate that go to one output. And at the beginning, I say that many times it's better to go beyond regular coordinate input. So, and if you remember, we said that many times when we train neural network, the neural network is performing a smooth approximation of the output. So in this case, if we have this sampling of this image and we train a ReLU network to map the 2D coordinates to the output, instead of getting this ground truth, we will get this low-pass version of the input. And the question is whether we can overcome this problem. So there is so our theory explained that. There is also the work on the spectral bias of neural networks that show that we basically, ReLU networks tend to learn low frequencies, and you get this phenomenon. So this is the ground truth, this is the final output. And the way to overcome this is to use positional encoding. It's some kind, you can think about it as a lifting strategy. So instead of just using the usual coordinates, you lift the coordinates using some frequencies. And there are many techniques to apply this this kind of lifting. One of them is like replacing the ReLU with sine function, and then you get like some harmonic activations that allow you to learn higher frequencies. Another way is to take the inputs and encode them with different frequencies. So these are examples of the different encoding techniques. So we have the positional encoding that take the coordinates, and then you take the coordinate again, and then the network get multiple inputs, where the first is the vanilla, the regular coordinates, and the second, the other inputs are basically different orders of frequencies that relate to these coordinates. So you get, for example, sine of x, sine 2 of x, sine 4 of x, sine 8 of x, and the same with the cosine. And another alternative is to use the siren strategy that replaces the ReLU with some periodic activations. So the position encoding basically take the coordinates p and encode them to a higher dimensional vector. Other encodings were used, but they lead to inferior results to the frequency-based encodings. So the Fourier features-based encoding, which are one of the best ones today, use basically cosine and sine with different frequencies, where the frequency depends on B. And B is selected randomly with some variance. So let's see an example. So for example, if we have this coordinate, so if the coordinate is here, so basically we get it. So if the coordinate is pi over 7, so basically we lift it to this 4-dimensional vector. If it's p over 6, we get this vector, and so on and so forth. And as I said, there are different type of encodings. So we can use Fourier features, we can use the radial basis functions. There is also the radial basis function grid. There is also a regular position encoding, which is basically frequencies that are aligned to the grid. And one of the advantages of Fourier features is that it allow you to learn higher frequencies. So in regular network, we have a spectral bias to the lower frequencies. So we get very smooth interpolation, but it misses a lot of the high frequencies. So at the beginning, if you remember this one-dimensional example that I showed you, it misses, because it is doing a smooth interpolation, it misses some of the frequencies of the network. Going to higher frequencies, encoding with higher frequencies allow you to get better construction of the image. But we have a problem. You can see that although we get here a better construction of the image, we have still some fluctuations. Things are not smooth as we want. And let's see with one-dimensional case, what is the problem here. So if you learn with the Fourier features, you can see that although the Fourier features is able to learn the high frequencies in a nice way, you get you don't get nice smoothness with low frequencies. So at the beginning, we say that when you train basically with the simple coordinates, we get here like nice interpolation. But with Fourier features, because you use more frequencies, you either focus on the low frequencies or you focus on the high frequencies. But when you have both of them, you lose in one of them. So this is the final output. You get these fluctuations, and the question how we can overcome this. And the same holds if you try different variances. So if you get low variance, you get something that is very smooth. If you get high variance, you get something that is very noisy. So we propose SAPE, which is a technique that tries to overcome that. And it has several components. So if we have a ReLU MLP, as I said before, you are good in learning the low frequencies, but you are bad in learning the high frequencies. With Siren, you have some fluctuation everywhere. And with Fourier features, you learn in a good way the high frequencies, but not in a good way the low frequencies. The question is whether we can enjoy both worlds. So SAPE, what we do in SAPE, we enjoy both the spectral bias, learning of the low frequencies, and the positional encoding by learning the high frequencies. So this is our method. You can see that we learn both the high frequencies and the low frequencies. So how we do that? So we first use a progressive encoding. Progressive encoding means that we start learning only with small frequencies. We have weights with the encoding, where at the beginning we give 0 weights at the end and high weight for the first encodings. So in our learning, at the beginning, we give high weight for the first encoding, then we increase the weight to the other encodings, and then we increase the weights to the last frequencies, which are the highest frequencies. So we learn at the beginning the lowest frequencies, and then a bit by bit, we learn the high frequencies. So you can, and one of the advantages of our method is that it's not dependent on the variance of the frequencies that we use. So here we can see the Fourier features, PSNR as a function of the variance and SAPE as a function of the variance. So you can see that we are more robust to this variance. Here is our result. This is the Fourier feature results, and clearly we get better results. Now the question is whether what we can do with tuning the rate, whether we want to increase the frequencies in a fast way or in a slow way, what is the correct thing to do. So the speed that you increase things impact how fast you learn frequencies. So you can see that when so it impacts the speed that you learn things, but and the question what we should do. So to solve that, we add the feedback to our network, and we recognize the following thing. If we look at this image, you can notice that in some parts of the image, we have very high frequencies, like here. In other parts of the image, we have lower frequencies, like this part. So basically, instead of using all of the frequencies in all locations, we can have a spatially adaptive learning, where we use positional encoding with low frequencies at this place, and positional encoding with very high frequencies at this place that require lots of high frequencies. So what we do, we take our network, we calculate the error of their construction at the point, we add the feedback, and then if the error is large, we add more frequencies. If the error is small, then we understand that we don't need to add more frequencies, and then the approximation there is smoother. So in places that have lots of fluctuations, we need to add more frequencies. In places that are smooth, we need to add less frequencies, and therefore we enjoy both worlds. And we have some map, and if you have something that is very dense, so you need to have this map that give you the exact the weights of the frequencies that you use. And because we sample the map sparsely, so if we get a new point that is not on the map, so basically we do interpolation between the points. So let's see some results. So for the silhouette case, so let's assume that we want to get a circle and bound it to this cat. So if we look at Fourier features struggles to fit the silhouette to the cat. If you look at SAPE, you can see that because we learn things in a spatially adaptive way, and we can support both the high frequency location and low frequency location, we learn the whole shape in a good way. So you can see that when we have no encoding, this part is learned in a very smooth way. But this part is not learned in a good way because we need high frequencies, and SEP is able to learn everything in a nice way. And here you can see many more examples for that. It applies also for images. So you can see here the Fourier features. Here you can see SAPE, and you can see that we can reconstruct the details in a much better way. It applies also to 3D occupancy maps, and you can see the heat map of the places that got high frequencies and low frequencies. And you can see here the construction that we get, the construction that you get with the Fourier features. You can see that we get much better results. Okay, and here you can see other results for 3D. You can compare it to Siren. You can see that we get the details in a better way. And we apply, and besides 3D reconstruction, we can apply it also beyond the implicit construction. We can apply it also to mesh transfer. The details are in the paper. We can take a mesh, transfer it to a point cloud, and then this point cloud get the style of the original mesh. Here you can see several examples with this mesh transfer with SAPE compared to the other methods, and you can see that improved results. So, due to the time, I will finish here and open the time or ask if someone has questions.